Ask one of these models how many times the letter R shows up in the word strawberry. There's a good chance it says 2. The real answer is 3. This is a machine that can write you an essay or debug your code, and it just miscounted the letters in a word a child can spell. That's not a bug somebody forgot to fix, and by the end of this, you'll see it was almost guaranteed from the very first step. The reason lives in something that happens to your text before the model does any thinking at all. Before a model sees a single word, that word gets chopped into pieces, and those pieces are called tokens. So here is the question I want to answer by the end. Why does a model that can write essays fail to count the letters in a word like strawberry? The answer is the very first thing that happens to your text, and once you see it, a whole pile of strange behavior suddenly makes sense. Let's go back to the machine we drew in the first episode. Text goes in one end, and the model predicts the next token out the other. But there's a step right at the mouth of that machine before anything else happens, and that's the step we are opening up today. Because here is the thing that trips everyone up. The model never actually sees your letters, and it doesn't even see your words. When you type a sentence, the first thing that happens is that it gets cut into pieces. Take "I love strawberry cake." You read that as a few words made of letters. The model gets handed a short row of chunks instead, and each chunk is a token. A token is just a piece of text that the model has agreed to treat as one single unit. Like a puzzle tile, it can't break down any further. Before we see how those pieces get chosen, let's understand why the model chops text up at all. You might think the obvious move is to give every whole word its own token. But there are millions of words, plus names, plus typos, plus every new word people keep inventing, so that list would never stop growing. And the moment someone typed a word that wasn't on the list, the model would have no way to represent it at all. The opposite idea is to use single letters as your pieces, so you only ever need a few dozen of them. That fixes the never-ending list problem, but now even a short sentence turns into a huge string of tiny fragments. The model has to do far more work to read the same text, and it has to rebuild every word from its letters every single time. So both extremes fall apart, one for having too many pieces and one for having too few. The answer sits right in the middle, and it's the whole idea behind tokens. Keep the common words whole because they come up constantly, and break the rare words down into smaller reusable parts. A word like "the" is so common it earns its own token, while a rare word gets stitched together from a handful of pieces. That way, the list stays a manageable size, usually somewhere in the tens of thousands of pieces, and no word is ever impossible to spell out. So who decides that berry is a chunk, but some random jumble of letters isn't? There's a little procedure that runs once before the model is ever trained, and it builds the whole list of allowed pieces from scratch. It's called Byte-pair encoding, and I'll run it on a tiny handful of words so you can watch it happen. We start at the very bottom with nothing but single characters. Every word is just a row of letters, and the only pieces we know so far are the letters themselves. Now the procedure does one simple thing over and over. It looks across all the words and finds the pair of neighbors that shows up most often. In our little corpus, E followed by S keeps turning up in newest and in widest. So that pair wins this round. And here is the move that matters. It glues that pair into one new piece, is, and writes it down as a brand new token. From this point on, is a single unit, exactly like a letter was a moment ago. Then it runs the same step again, on words that already have the new piece merged in. Next, it might glue is and t into ist, because that's now the most common pair. Then L and O become low, and low and W become low. Every round it merges the most frequent pair, and the list of known tokens gets a little longer. Do this a few thousand times over a mountain of real text, and the common chunks bubble up all on their own. Whole common words end up as single tokens, and the rare stuff stays broken into smaller pieces without anyone hand-picking a thing. Now we can finally solve the strawberry mystery, and I want to show you the real thing, not a cartoon. Here is the word strawberry run through an actual tokenizer. It does not come out as 10 letters. It comes out as 3 pieces, straw and berry. That is all the model ever receives, just those 3 chunks, and the individual letters are already gone. So picture what we are actually asking the model to do. We want it to count the R's, but it never sees an R. It sees straw, berry, and the R's are buried inside those chunks where it can't look at them one at a time. Counting letters inside a token is like counting bricks in a wall you're only allowed to see from across the street. It's not that the model is bad at counting, it's that we took the letters away before it ever got started. And it gets even starker than that. When the word shows up in the middle of a sentence, the tokenizer often packs the whole thing into one single token. So a lot of the time, the model sees strawberry as one solid blob with no seams in it at all. Either way, whether it's 3 chunks or 1, the letters were never on the table. Once you know this, a whole pile of weird behavior stops being mysterious. Take a rare word like an unusual place name the model barely saw while it was training. A common word arrives as one clean token, but this one shatters into 4 or 5 awkward pieces. The model has to reassemble the meaning from fragments, so it's clumsier with rare words than common ones, every single time. Numbers are the same story, and this one catches people off guard. A long number doesn't come in digit by digit like you'd hope. It gets chopped into oddly sized groups, so a long number might arrive as one chunk of digits, then a shorter one, then another, split in places that make no sense. The model never sees clean place values, and that's a big part of why arithmetic can quietly go sideways on it. Here is my favorite one because it feels almost unfair. The same word with a space in front of it and without can become 2 completely different tokens. To the model, strawberry at the start of a line and strawberry after a space aren't the same thing. None of these are separate bugs that somebody needs to go and fix. They are all the same single fact wearing different costumes. The model reads tokens, not text. So let's answer the question we started with. Why does a model that writes essays miscount the letters in strawberry? Because before it read a single thing, we cut the word into set, raw, berry, and handed it the pieces instead of the letters. It isn't thinking about spelling at all. It's working with chunks we chose for it long before it ever woke up. This is step 1 of the whole machine. The very first thing that touches your text, and everything the model does is built on top of it. But there is still something missing here. Right now, a token is just a chunk of text with a number stuck to it, and a bare number like that means nothing on its own. So next time we take these tokens and turn them into something the model can actually reason with by giving each one a position in a kind of meaning space. That's the step where berry and fruit start to live near each other, and the machine finally begins to understand.